In this video, we will discuss about Newton's first law. Better known as the Law of Inertia, is a fundamental rule that governs everything in our universe. The law states a simple truth. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless it is acted upon by an unbalanced external force. To understand this, let's look at three key pillars. First is inertia. Think of inertia as an object's stubbornness. It is the natural tendency of any object to resist a change in its motion. If it's sitting still, it wants to stay still. If it's moving, it wants to keep cruising. Second is mass. Mass is how we measure that stubbornness. The more mass an object has, the more inertia it possesses. This is why pushing a heavy truck is much harder than pushing a small bicycle. More mass means more resistance to change. Third is the net external force. This is the game changer. Without an external push or pull, like a kick or friction, an object's state will never change. This force is what finally breaks inertia and causes an object to speed up, slow down, or turn. We see this law in action every day. When a car stops suddenly, your body jerks forward because your inertia wants to keep you moving at the car's original speed. A coin sitting on a card stays exactly where it is when you flick the card away, because its inertia keeps it at rest. On smooth ice, a hockey puck slides for a long time, because there is very little friction or external force to slow it down. In the deep vacuum of space, where there is no air resistance at all, a rocket will travel in a straight line forever once its engines are off. Now, let's look at how these principles play out in the real world and the data that defines them. First, consider these everyday examples of inertia. In a car, safety is key. When the vehicle changes speed, the seatbelt provides the necessary force to keep you secure and in place. Next is the classic coin flick. When you flick the card away, the coin maintains its state of rest due to inertia and drops straight down into the glass. On the ice, a hockey puck moves easily because of low friction, leading to prolonged motion across the surface. And in the vastness of space, where there is no external force like air or friction, a spacecraft will continue at a constant velocity forever. To understand the science behind this, we look at the net external force data. When forces are balanced, the net force, or F or net, equals 0. In this state, acceleration A is also 0, and the velocity v remains constant. This means the object will either stay still or keep moving at the exact same speed in a straight line. However, when forces are unbalanced, the net force, F or net, is not 0. This imbalance causes the velocity to change, meaning acceleration A is now present. This is the moment when an object speeds up, slows down, or changes its path. Common misconceptions and mathematical context. To truly master Newton's first law, we must clear up some common misconceptions. Many people believe that objects naturally come to rest on their own. But in reality, objects only stop because of external forces like friction or air resistance. Without these forces, an object would slide forever. Another common myth is that a continuous force is needed to keep an object moving. This is incorrect. Once an object is in motion, no force is required to maintain that state. Force is only needed to change that motion, such as making it go faster, slower, or turning it. Now let's look at the mathematical context. The relationship is defined by the formula F net is equal to ma. This shows us that when the net force, F or net, is 0, the acceleration A must also be 0. Consequently, the velocity v remains constant. We can also express this through calculus. If the net force is 0, then the rate of change of velocity, or d over dt, is 0. This confirms that the velocity is constant and unchanging. Finally, remember the role of inertia. Mathematically, mass, m, is directly proportional to resistance. The greater the mass, the greater the inertia, and the more force you will need to disrupt that object's steady state. Derivation and why it matters. To see the logical perfection of this law, we can actually derive it from Newton's second law. Starting with the formula, F net is equal to ma. We see that if the net force acting on an object is 0, then the product of mass and acceleration must also be 0. Since mass cannot be 0, the acceleration, A, must be 0, leading to a constant velocity, v. Using calculus, we express force as mass times the rate of change of velocity, or Frim duoaditi. When force is zero, the derivative of velocity with respect to time is zero, which mathematically proves that velocity remains constant. This elegant derivation was first shared by Newton in 1687, in his groundbreaking work, Principia Mathematica. But why does this law matter so much? First, it defines inertial reference frames, which are the very foundation of all mechanics. Second, by introducing the concept of inertia, it revolutionized how we perceive the physical world. Third, it successfully challenged Aristotelian physics, sparking a scientific revolution that changed history. Fourth, it serves as the essential foundation for momentum conservation, a pillar of modern physics. And finally, it has vital practical applications, from designing vehicle safety systems, like airbags, to navigating spacecraft through the stars. Newton's first law is the engineering key to our modern world. Newton's first law, the complete guide. As we conclude our journey, let's look at the complete picture of Newton's first law. At its heart, the definition is clear. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This entire behavior is driven by three concepts: inertia, mass, and force. When we translate this into formulas, the math is precise. If the net force, F net, is zero, velocity, V, remains constant. Using the relation F r ma, we see that without force, there is no acceleration, A, da frac dv dt, da, zero. This simple equation is what keeps the universe predictable. Our real-world illustrations bring this to life. Whether it's a car passenger's movement, a coin dropping after a flick, a puck sliding on ice, or a rocket traveling through the stars, inertia is the silent force behind them all. To remember the key points: objects naturally resist any change in their motion. Mass is the physical measure of that inertia. Only an unbalanced force can change an object's state. And remember, no net force means a perfectly constant velocity. From life-saving safety systems and space, exploration to sports and modern engineering, Newton's first law isn't just a classroom lesson. It is the fundamental rule that moves our world. Thank you for exploring the law of inertia with us. Keep questioning, keep learning, and stay in motion.